Jeremy's weight for the past 4 months is shown above. Jeremy makes this statement: I have never in my life weighed 200 pounds. Based on the data above, is this statement true or false?
Maybe he never weighed.
Okay, so we're pretty much saying false, right? Because we see in February he weighed 199, and then in March he weighed 203.
Maybe he means he never stepped on a scale.
So we don't have evidence here that said at this time he weighed 200 pounds, but we would be like, Jeremy, come on, you weighed 200 pounds at some point. You weighed 199. Now you're at 203. You had to weigh 200 sometime in between there, right? I mean, I guess even if we're getting like super technical, like because your weight will fluctuate, maybe like as you eat something, but it's still sort of like, I guess at one point you hit 200, right? So we would, for the most part, at the very least, Jeremy's statement is very misleading, right? Because if you say, I have never in my life weighed 200 pounds, we are assuming that means you never got above 200 pounds, right? Because if you were ever above 200 pounds, then you were at 200 at some point, right? His statement is at the very least very misleading because weight is something that we consider to be continuous, right? So you don't go from, even if you're like a wrestler cutting weight and you're like running with trash bags on and sweating, you're losing that weight gradually. It might have came off very quickly. Like that morning you might have weighed 200 pounds, and that afternoon you might weigh 195, right? Which is unhealthy. Don't do that. You guys aren't wrestlers anyway, are you? Anyway, wrestlers, don't do that. It's terrible for you. But that weight came off, even though it was in a very short period of time, it came off gradually, like sweat drop by sweat drop. You're sweating that out, right? So we consider weight to be continuous. So we would say since weight is continuous, and Jeremy weighed 199 in February and 203 in March, he must have weighed 200 sometime in between. Right. Now he might have his weight might have went up to 201 and then back down to 198 and then back up to 205 and then down to 203. We don't know what happened. He might have weighed 205 times in between that time period, right? Because weight certainly is something that can fluctuate. But because we're considering it to be something continuous, it had to be something that, crossed that value. This is what we're learning about today. It is the intermediate value theorem. It's a really simple principle. But it is something that we have to look at from like a logical mathematic principle. The intermediate value theorem sounds complicated, but basically it's going to say if Jeremy weighed 199 and now he weighs 203, he had to weigh 200 at some point in between, right? So intermediate value theorem says if f is a continuous function on the closed interval from a to b, and d is a number between f of a and f of b, then the intermediate value theorem guarantees that there is at least one number c between A and B such that f of c equals d. Now that sounds really complicated when like you read it all together. But let's look at a picture that goes with this, because I think the picture really helps you to see what's happening here. So f is a continuous function on the closed interval a to b. So on my x-axis here, I'm going to label a point A and a point B. D is a number between f of A and f of B. Which axis is f of A and f of B on? That's our y-axis. It's labeled f of x right here, right? So let's say I'm just going to draw a function here. It could look like anything, as long as it's continuous, as long as we don't have holes or asymptotes. So like f of A would be right here, and f of B would be right here. And so D is a number between those. So we're going to put D right here somewhere. So the intermediate value theorem guarantees that if we have this setup right here, there has to be at least one number C between A and B, that's on the y-axis, x-axis, such that f of C equals D. Okay, this is all this is saying right here. I'm going to draw me a little dotted line here for D. It is saying somewhere between A and B, you have to reach that value. If you have your f of A is here, your f of B is here, D's in between, you got to cross that line to get there, right? This has to be true if this function is continuous. Now, if the function is not continuous, it's possible for you to have like a jump where you don't ever actually equal that, right? So that is possible. So, here's an example of where we can use the intermediate value theorem. Okay, now, it is really important. What is the condition that has to be true for us to even apply the intermediate value theorem? F must be continuous, right? So, we must first show or state that F is continuous. E to the 2x minus 5, is it continuous? It is continuous. Exponentials are continuous everywhere, so there's nothing there that would cause a discontinuity. So f of x is continuous. You can say on -1 to 2, or it would be okay to say here, it would be okay to say for -infinity to infinity, because it is continuous everywhere. So you could say either one of those. It only has to be continuous from -1 to 2, because that's the only interval that we're looking at. So if it did have a discontinuity, but that discontinuity was outside of that range that we're, or domain that we're looking at, then it'd be okay. So, if I find f of -1, okay, that would be e to the 2 times -1 minus 5, which is e to the -2 minus 5. What do I do with negative exponents? Go to the bottom, right? So it's 1 over e squared minus 5. Now, I'm not using a calculator on this, so I don't know exactly what that is. But I do know e is like 2.718. So this is 1 over 2.718 squared. Is this value going to be positive or negative? It's going to be negative, because I know 1 over e squared is going to be like a pretty small fraction. that is smaller than 5. So when I subtract 5 from it, I should get a negative. So I'm going to make myself a note here. That's less than 0. Even though I don't know exactly what the value is, I know it's less than 0. Now, if I find f of 2, right, e to the second squared minus 5 is going to give me e to the fourth minus 5. Again, I don't have a calculator. I can't tell what that number is exactly. But if I take 2.718 and raise it to the 4th power, is that number going to be bigger or smaller than 5? Bigger than 5, right? So this is a positive number. So if we think of what's happening here, if we like sketch a graph, I know at -1 here, I've got some sort of negative value, right? And then I know over here at 2, I've got some sort of positive value. Okay? I also know that f is continuous. So the question asks, do I have a 0? What's a 0? Remind me. What is a 0? X-intercept. So, if I have a continuous function, and I've got to go from down here somewhere to up here somewhere, I've got to cross that x-axis somewhere, right? I don't know where it's at. I'm not even asked to find it. I'm just asked to prove it has to be there, right? So, I would say here, by the intermediate value theorem, since, all right, now I do not know exactly what f of -1 is, like a decimal approximation. But I know f of -1 is less than 0, and that 0 is less than f of 2. Right? Basically, I'm saying 0 is somewhere in between these two values. Right? I've shown up here what they are, so I've shown that I know what they are. Now I'm saying that 0 is in between these. So by the intermediate value theorem, since 0 falls between these two values, there must be some C value such that -1 is less than C, less than 2. It's okay, I think, to use an X there. They just use a C a lot of times to show like it's a specific value. But if you use an X, if you say there's some X such that -1 is less than X, less than 2, that's probably okay too. Some value such that C is between -1 and 2, and f of C equals 0. We should add the conclusion, thus f of x has at least one 0 on -1 to 2. And we need to start our quiz. So we're going to do some more of these tomorrow. You're not going to do the intermediate value theorem assignment tonight because we have not done enough of it yet.